Hello, everybody. Welcome back to my lecture series on sustainability issues in energy. Today, we are going to finish up our unit on geothermal energy by tackling high enthalpy geothermal systems, enhanced geothermal systems, and the topic of induced seismicity. As always, if you've been enjoying these lectures, I invite you to subscribe to my YouTube channel, and you'll get notifications whenever I publish a new one of these videos. All right, so let's start out by talking about high enthalpy geothermal power. So this is situations where the subsurface is very hot, fairly close to the surface. So very high geothermal gradients. And in these situations, the water that is produced from geothermal wells actually is entirely, or at least partially, in the form of steam. And if you're producing completely dry steam with no liquid water, you can feed that directly into a turbine to generate electricity. If there is a little bit of liquid water in there, we would call that wet steam. There are ways of separating that out, and again, using the steam to generate electricity. So let's talk about that a little bit. Here's a nice photograph of some steam power generation in Iceland, which is probably the spot that's best known for that. All right, so here's our temperature entropy diagram for water. And the general rule here is that if your reservoir temperature is above 300 degrees Celsius, then you're going to be producing dry steam. So here's 300 degrees Celsius. And if we move over here, remember that atmospheric pressure is about 0.1 megapascals. So when you bring that steam up to the surface, it's going to be completely dry steam. If you're in the saturated, in the liquid vapor region here, you're going to be producing more, wet steam. But obviously, here's the boiling point of water at 100 degrees Celsius in one atmosphere. So as long as you're up and to the right of that, you're going to be able to produce dry steam. Lower temperatures, yeah, you'll produce wet steam, which is a mixture of steam and water, which is still useful. High enthalpy regions are going to be regions with high heat flow and correspondingly high geothermal gradients. Here's a map of the heat flow around the world. And what we're looking for are the areas that are red. So these are areas where there's very hot rock, very close to the surface. The trend generally follows the mid-ocean ridge system. Mid-Atlantic ridge really pops out here. East Pacific rise, all that good stuff. Juan de Fuca plate up here. These are going to be areas where you can produce, do high enthalpy geothermal. Now, because most of these areas follow the mid-ocean ridge system, they're going to be underwater. But there are a few spots where you can do this on land. The most famous, obviously, is Iceland. Some parts of the western United States also have steam production. The Geysers in California is a good example of that. And there's a few other places around the world where you can make this work. So high enthalpy wells are designed a little differently from hydrothermal doublets in that it's almost like you're producing oil or gas from the subsurface. You're just producing steam. And so there'll be, a series of different casing strings that you go down to get down to your production interval. And you typically produce the steam through these perforated liners. Here are some examples. You can see the perforations in these pipes. And so the steam flows into the pipe and then back out to the surface through the well. So it's a fairly simple well construction, and that's how it works. Now, generating electricity from steam is pretty straightforward. So if you've got dry steam, what will happen is here's your well, steam comes out, goes directly into a turbine. It loses heat, obviously, and you'll have the steam condense into water. And so what comes out here is the shaft, which drives the generator, and then you get electricity. But you also have hot water, and that hot water can be used for all kinds of other stuff, including district heating, There's you can use it for greenhouses to grow, fruits and vegetables when it's cold. So, all kinds of interesting stuff you can do with that hot water. Here's an example of a dry steam generation at the Geysers. This is in Northern California. So here the Geysers were producing dry steam from wells that are about 7,000 to 8,000 feet deep, and they're around 300 degrees Celsius, which is that minimum threshold that you need to, maintain having dry steam come to the surface. So they bring the steam out, it generates electricity, and then they re-inject the cold water for it to heat up again and start the process. The Geysers have been operating for a very long time, and it's a pretty good operation. Now, if you're at a slightly lower temperature and you're producing wet steam, you have to use a type of power plant called a flash steam power plant. And the really only difference here, composed to the dry steam case, is that you have to have a gas water separator to take in the wet steam and get just the steam by itself out to the turbine. And separate out the water. And this water that's separated will then mix with the effluent from the turbine. And then same thing, you can use that hot water. Generators over here, and it provides electricity. So slightly different setup. Here's a flash steam power plant in Iceland. So you can see here's the wet steam coming in from the geothermal wells. And here's the separator. Let's see, the steam comes in here to the turbine hall, and then the water gets disposed of somewhere over here. So a little bit different setup, but same general idea. Okay, now what if you're not fortunate enough to be located in a high enthalpy region, but you still want to generate electricity with some really, really hot fluids? So that means you have to drill really deep to get access to those fluids, like 150 to 200 degrees Celsius, we're talking. So in this case, you're going to want to look at enhanced geothermal systems. Enhanced geothermal systems function similarly to a hydrothermal doublet. Except in the case of a hydrothermal doublet, you're tapping into a reservoir of warm fluids that has good porosity and good permeability. So you're relying on the flow of those fluids from the formation into your well and then back down and into the formation. With enhanced geothermal, you drill very deep into crystalline or metamorphic rocks that typically have very low porosity and very low permeability. But they do have fluids and they're very hot. And so what you have to do is you have to exploit naturally occurring fractures that are in those rocks. So these are the characteristics of enhanced geothermal systems, typically above 200 degrees Celsius, deep, low porosity rock, granite, that sort of thing. And you're either going to produce through natural fracture systems or induced fractures. So there does have to be some fracture stimulation in enhanced geothermal systems typically. So EGS fracking is a little bit different from fracking that we use in shales to get oil and gas out. Okay, we're generally not going to be generating new fractures in EGS. What you're doing is you are widening or reopening existing fractures. Okay, and these fractures are typically then not propped. So here's how it works. So let's imagine you've got an existing crack in your rock that is not aligned with the maximum principal stress. If you think back to your rock mechanics, if this is a shear fracture, typically it's not going to be aligned with the maximum principal stress just because of the angle of internal friction effect in a more Coulomb sense. But it can also be possible that this fracture formed in a different state of stress than we have present day. So anyway, you've got a fracture that's not aligned with the principal stress field that we have. So you pump a pressurized fluid into this fracture, which causes it to open. Now, it initially opens normal to its orientation. So you just have, straight up opening in that direction. But then because of the background stress field, you'll have a little bit of slip on that fracture. And so what happens is the asperities on this fracture get misaligned with each other, and that allows the fracture then to close up, but not all the way. And so you've got these void spaces now that can allow for better flow of fluids and better geothermal energy production. The fracking process, it's very similar to what you have in oil and gas. You pump high pressure fluid into the well, and it's typically water with some additives in it, friction reducers. You can add acids if you want to do a little bit of mineral dissolution in the fractures to try to increase the permeability. But that's, that's pretty much all there is to it. Here's what the pressure response looks like when you're doing this. Now, on the left here, this is the pressure response that you would get if you were generating a new fracture, okay? So you increase the pressure and you reach your fracture pressure here, which is the pressure required to generate a new crack. And then the crack expands, the pressure bleeds off a little bit, and then you shut in the well and allow that pressure to dissipate. Okay, so that's what happens when you're generating a new crack. If you're doing an EGS stimulation where you're just widening existing fractures, you don't have to generate the crack to begin with. So you don't have that spike there. So you widen the fracture, and then again, you shut in the well and let the pressure dissipate. And so that's what it looks like. So then how much of the rock actually gets stimulated? Well, you can stimulate pretty large volumes of rock. This is a study that was done in Subsurface in France, which is a big geothermal area. And they did what's called microseismic monitoring here to listen to the little seismic events when the fractures are reactivated. And you can locate those events in space, and you can see that, this depth axis, this is in kilometers. So as are the northing and easting axes. So you can see you get, many cubic kilometers of rock stimulated. So you can get very large, fracture fields that contribute a lot of flow to the well. You can see that these stimulations were done over a period of 12 years. Because what happens is eventually, once you reopen a fracture, it'll eventually close itself back up. And so you periodically have to go back and re-stimulate these wells. Enhanced geothermal, typically you're going to run the hot water through a heat exchanger to generate your electricity. So it's going to look something like this. You'll have typically a production well and a disposal well to make this work. Okay, now there's a lot of talk in the news right now about these, ultra super wicked deep geothermal wells, like 20 kilometers deep. The purpose of drilling wells that deep is to access supercritical water. So critical point of water is 374 degrees Celsius, 22 megapascals. And the thing about supercritical water is that it behaves like a very dense gas. It has a gas-like viscosity, but a liquid-like density. And the combination of those two properties mean that it flows very easily. There's very little in the way of frictional loss, and the pressure gradients don't have to be very large to get it to flow. But the liquid-like density means that it's going to have a very high heat capacity. So you can flow easily, carry a lot of heat. And if you're using supercritical water, you can get about 10 times more useful energy than with conventional geothermal. So this is a goal right now because you can get much better amounts of energy generated if you can drill down to the point where you've got supercritical water. There are a lot of problems with this, but the main ones are that if you're drilling in something that's that hot, you really can't use standard drilling, parts, okay? The pipe gets really bendy at that temperature. The bearings break down, electronics fail. You have to come up with a totally new design of your equipment for that to work. The other problem is that ultra deep rocks are very hard, much harder than shallower rocks. Bits don't last as long, partly because of the hardness of the rocks and partly because of the temperature. And, just from a cost and timing standpoint, if you're down 10, 15 kilometers and you're having to switch out your drill pipe every 100 meters, it's going to take you years to drill that well. So maybe you want to think about a different drilling technology. And in fact, there's a couple of alternative technologies that are being investigated right now to alleviate these issues. They include lasers that melt the rock, millimeter electromagnetic waves that also melt the rock, and then plasma that's actually used to break up the rock. These all work pretty well. There's some drawbacks. Lasers suffer from scattering and energy absorption from the dust that they create when they break up the rock. And they're expensive and require a lot of energy input. Millimeter waves have a lower energy requirement and don't have the problem with scattering and absorption. Plasma has a very low energy requirement. So there's a lot of work, like I said, being done in these areas. Here's some millimeter wave tests from DOE project back in 2014, just investigating how these things work. So you can see that they tested, granite, basalt, limestone, sandstone, and you can melt, these holes in the rocks. Obviously, if you look at the time scales that were used here in the lab, takes a very long time to melt a small amount of rock. So presumably you'd have to put in a much higher energy input to get this to work. But this is an ongoing area of research, which is pretty cool. There's a company called Quays right now that is, still working on this technology, and they hope that it'll be deployable soon. One of the cool things about millimeter wave is that when you use it to drill through the rock, actually what happens is that the rock gets so hot that it gets turned to glass. And so the wellbore will be surrounded by, they call it a vitrified wall. So it's a very durable, very hard coating to the well, which actually helps with the wellbore stability. Plasma drilling is another area that a lot of people are working on. There's a company called GA Drilling, which got a $20 million investment from Neighbors, which is one of the largest drilling contractors. And they're aiming for a field test in 2023. Same thing there, you're breaking up the rock by, inducing plasma channels in it. So it's a pretty cool technology. So we'll see where this goes. I think it's pretty promising in terms of getting these ultra deep holes drilled. Okay, there's a couple of issues related to geothermal wells that we do need to talk about. One is the fluid chemistry and the fluids that you produce, and the other one is induced seismicity, which is kind of a big one. So subsurface fluids contain a lot of dissolved chemicals. Geothermal fluids are particularly hot, and so they contain a lot of dissolved species. These include things like chlorides, carbonate, bicarbonate, sulfate, silica, that sort of thing. Here's an example of Mammoth Hot Springs in Yellowstone National Park. This is travertine that's naturally being precipitated from the CO2 that's dissolved in the water as it comes to the surface. This is Grand Prismatic Spring. Again, the bacteria really like to live in here, and they're what give the spring its color. But there's all these mineral deposits and bacterial mats around here too, related to all the delicious things that are dissolved in the spring water that the microbes like. The issue with geothermal fluids is that they're hot, and that means that they can carry a lot of dissolved materials. Salts typically have higher solubility at higher temperature. So when you take a hot fluid with dissolved salt in it and bring it to surface, as it cools down, more and more salt will precipitate out. So you can see here, this is solubility versus temperature for a bunch of different salts. And you can see that, they all decrease fairly rapidly with temperature. And what happens is that, the inside of your pipes and stuff can get this salt build up in it. It's called scale. This can include radioactive salts. This is definitely something you want to avoid. So to alleviate scale problems like that, you can do detailed fluid analyses, do a very careful system design with carefully controlled pressure temperature paths, so that you're minimizing places where there are sudden pressure drops or supersaturation. You can also use materials with scale resistant coatings and that sort of thing to try to slow down the rate at which scale develops. But you also have to acknowledge that scale will form. And so you need to have an intervention plan and a monitoring plan to make sure that you solve problems before they become really big problems. Okay, here's an interesting study that shows the hazards of subsurface gas in drilling geothermal wells, okay? And this also highlights some of the induced seismicity hazards that you have. So this was an event that happened in northeastern Switzerland in St. Gallen, where there was earthquakes that occurred in close proximity to a deep geothermal well. And you can see that there were a couple of, magnitude 3 earthquakes that occurred. So this is a map of a bunch of different seismic events that happened. And this is a nice paper by Spinden et al., where they go through what they think happened. So what happened was there was a geothermal well that was drilled through into the Malm, I believe that's Upper Jurassic, to access very hot fluids. You're looking at 4.2 kilometers depth here. And what happened was that they attempted to do a stimulation to open up some fractures. So initially, they pumped water down the well, and the water found a high permeability fracture zone. And they think it went down here to a low permeability zone that apparently was sealing a gas layer. So what happened was the high pressure fluid leaked down this conduit here, and it activated some faults directly above the gas. These faults actually may have been sealing in the gas, and they got reactivated, so they suddenly became permeable. And then what happened was gas started flowing back up the fracture zone. And so this is all of a sudden a big problem, because you don't want gas coming out of your geothermal well. So this is just an example of how EGS stimulations can go wrong. This is an orthogonal cross section along this fault plane here, so you can see the evolution of the gas coming out of these lower zones down here. And the corresponding increase in seismic activity. So, we generally don't like to have earthquakes happening. And so we try to do things to try to avoid that. So induced seismicity is a big problem with enhanced geothermal systems. And the reason for that is, if we go back to this diagram, anytime you've got slip along a plane of weakness, you will create an earthquake. It might not be a very large earthquake, but that's what's going to happen. And this often happens in EGS stimulation, because that's kind of what we're trying to do, right? We're trying to get the fracture to slip a little bit so that it will close up and stay open this time. So here's why pumping high pressure fluids down the well can cause shear failure. So here's our Moore Coulomb diagram. So here we're plotting effective normal stress on the x-axis and then shear stress on the y-axis. So if we're initially here, stable, no failure, there's our Moore circle, and I increase the pore pressure, what's going to happen is that the Moore circle is going to move to the left, because remember, we're subtracting the pore pressure from the total stress. So a higher pore pressure will mean a lower effective stress. And you can move that Moore circle far enough to the left that you intersect the failure envelope just by increasing the pore pressure. And so this can happen during EGS fracking or even just during fluid injection to do subsurface heat exchange. So this can be a big problem that we have to be aware of. Now, we quantify the magnitude of earthquakes using two different scales. There's the Richter scale, which we're probably all pretty familiar with, but then there's the Mercalli scale, which describes the sensed or felt magnitude, whereas the Richter scale is based on the energy released by an earthquake. So here's the modified Mercalli scale. You can see it's done in Roman numerals, goes from 1 to 12, and it maps roughly onto a Richter magnitude. So, things like, so I mentioned in the St. Gallen case, there was, 3.5 magnitude earthquake. That's approaching a Mercalli magnitude 5, which can break windows, break plaster walls. This causes damage, and so we don't want to have that happen. Now, as far as the Richter magnitude goes, this is an energy release, and it's the moment magnitude is what we typically use for this. The moment magnitude is given by this equation here from Kanamori, and it's given as a function of the seismic moment, which is the product of fault rigidity, the average displacement along the fault, and then the active surface area of the fault. So this shows you that smaller surface area and smaller slip will give you lower magnitudes, and that's how the Richter magnitude is related to the amount of slip and the area of slip. So we define microseismicity as generally things that are lower than magnitude 2. Okay, so these are, maybe you might feel it when you're sitting in a chair. It might just be detectable by sensitive instruments. That's what microseismicity is. Anything above that is things that people start to feel. This is a table of some, seismic events from different geothermal projects around the world. You can see most of these are less than magnitude 3. So you might not notice them, or you might notice them, but some of them are quite large. So there's the St. Gallen event there, 3.5. The earthquake at Basel in Switzerland is very well known because that occurred in a heavily populated area, and it very strongly influenced public perceptions of geothermal projects. Let's see, Pohang event in South Korea, same thing. That was, I think there was at least one fatality associated with that. There was a magnitude 4 at the Geysers. Interesting, there was this magnitude 3.7 in the Cooper Basin project in Australia. And when you look at, public perceptions of these things, that one didn't really influence public perception at all because it was in the middle of nowhere. Nobody felt it, or very few people felt it. And so it didn't have as big an effect as something like Pohang, which was in a highly populated area. Let's put a very negative, put geothermal in a very negative light in South Korea. So, it's important to realize that induced seismicity is often unavoidable, and you've just got to be very careful about how you stimulate these wells and be mindful of how the public is going to respond to events when they occur. Okay, well, that's it for geothermal. I hope you've enjoyed all these lectures. Stay tuned to the next one because we're moving on to hydrogen. I think you're all going to like it. So we'll see you next time.